Hello my friends, welcome again to my video channel. We will continue our series about the scope HM605, and as promised at the end of part 2 we will find at least one crazy topic. Let's start. Meanwhile, the new coupler arrived. The old plastic coupler which was broken is replaced by a new one, by a metal type. It fits, but it's a question of millimeters. I had to cut off a small plastic piece from this switch, because when I take out the this switch, it's a 10 time base times 10. So this touches a little bit the switch, doesn't matter. This is a position fine setting, and we also have a coarse setting. But this switch times 10 and back is times 1. It also works. All boards, switches, the mechanic is reinstalled, all plugs are in, the new electrolytics are in place. Now let's do a check, and I think we have to focus on the last topic. I will show it. We have signal connected, 1 kHz connected to both inputs. Both channels are identical. Shift is okay. Position, the fine setting is also okay. And when I use times 10, the mode is alternate. Can also use job mode. All works. There's only one problem, and this is the indication here. It is called overscan. These LEDs, there are 2 LEDs in the shape of an arrow, and they should be lit when the picture is overdriven. That means in this direction, or also overdriven in the negative direction. Even by position, nothing happens. Nothing happens. Or by amplitude, when I increase the amplitude, nothing happens. The LEDs are dead. So I will look at this circuit, which does it. There's a comparator in it. The comparator measures the voltage drop in the final amplifier and the vertical amplifier, and when the peak of the signal is over a certain limit threshold, then these LEDs are lit, but as we see, nothing happens. This is a vertical amplifier output. These 2 transistors are connected in a common base circuit. The base is grounded, high frequency ground, and this the level of the base is set to approximately 12 volt. The anode voltages here is 68 volt, and these 2 transistors are driven via the emitter. This is a low ohmic circuit, typically for high frequency applications, to prevent oscillations. We have seen it can oscillate when we have here a wire which is too long, but in general such a circuit is proof against self-oscillation as long as it is treated reasonably. We have here the 2 driver transistors. These transistors are also they're the common emitter circuit. Yes, the emitters are grounded by the base, driven by the base, and the collectors are connected to the emitter. And here we have the connection, this line input to this comparator, and the other line is the input to this comparator. These 2 comparators measure the voltage drop across the resistor in the emitters, and when one of the transistors gets conductive to drive the transistors, there is more voltage drop here or here, more positive or negative voltage drop, and this drives the two comparators. Here we have a monoflop, two monoflops with a time constant, and they drive the two transistors, and here we have the two diodes. And this circuit is obviously dead, nothing happens, this works, but from this point here via the comparators, it is one comparator, TL820CN, Charlie November. These two comparators are in one case, and they drive one monoflop. There are also two monoflops in one case. But nothing happens here. So first I have to look at the circuit, what's going on there. Here we are again in the final output stage. Here we have the power transistor, the output to the CRT. And this part behind this aluminium profile here, this part is the comparator. Here we have pots, I think it's for the thresholds. And the two circuits, the comparator here and the monoflop. I see something what I have never seen until. First a remark, I do not prepare any scopes or other equipment to make videos. What you see here is reality. Hard to believe what you will see now. But it is as it is, and I show it to you. And then we can discuss it. I changed the point of view. Here we have the monoflop and here we have the comparator. Maybe you see it now. I turn it a little bit around. Do you see this? The two pins are hanging in the air. Yes, you can see it. There's a comparator here. Something happened. It is not seated correctly or whatever it is. I will take it out and check what happened. And again, that's reality, not a fake. This scope is heavily mistreated. I don't know why, don't know what happened, who it was. No idea. The situation is getting more and more crazy. The comparator TL820 Charlie November was an SN74LS123N. It has 16 pins. The comparator has 14 pins. That was the reason why two pins were hanging in the air. The other IC should be the SN74LS123N. That's correct. This was here, that's correct. But this was here and this is not correct. Absolutely wrong IC. I do not know what happened. Maybe someone did not realize which circuit, which IC has to be where. Maybe he wanted to repair it and made a mistake, but when I see that the number of pins is not correct, when I replace an IC with wrong number of pins, this should be a signal for my brain to say, something is wrong. Obviously the guy had no brain, no idea. Well, first I will check whether the monoflops are working and the LEDs on the front panel I will trigger manually by hand. I leave this socket with the comparator open. I only check the monoflop. This is possible, and then I will see whether there's a problem with the monoflop and the driver for the LEDs, or whether we have really only a problem with the comparator. We have here the 74LS123, and this monoflop is triggered via input A. This is input A here, and also here with a negative pulse, because the input is inverted. There's a dot, here's also a dot. We have an inverted input, so we need a negative slope to trigger it. I assume there's an internal pull-up resistor in the monoflop, so this voltage here should be high, and when I connect it to ground, I will use a 1 kilo ohm resistor or some 100 ohms to limit the current if there's any fault. Then it should be possible to trigger this one and of course the other one. This is the overscan in positive direction. That means when the trace is moving upwards, and this is a scan for the low voltage when the trace disappears in the bottom area. So I will check it now and measure first the voltage at pin 9 and also at pin 1, and this should be high. I measure the voltages at the monoflop inputs. We have 2 volt per division. At pin 1 I can measure a voltage of 1.5 volt, and at pin 9 I also measure voltage 1.5 volt. It seems to be a little bit low for TTL, but these open inputs, I think these are emitter inputs when I have a look into the data sheet. So high is specified something between 2 volt or so, plus minus, and low is specified 0 dot something voltage. So this could be high. I will check it now with a ground connection whether I can trigger them. I use a short wire with a resistor 1K. I connect this to ground, and then I will tap this onto the pin and see what happens, and have a look at the 2 LEDs, overscan, positive and negative direction, and now we can see that it works. First connected to pin 1. Pin 1 is the negative side. Sorry, not a good contact. And when I go to pin 9, we see it's a positive side, so this works. So the monoflop side is okay. We only have a problem with the comparator side. The comparator is not existing. There was a wrong IC in it. And now I have the problem. This integrated circuit TL820 CN is not available on the market. Even a data sheet I couldn't find in the net. Some companies are offering this IC, but they are asking for contact, and I'm quite sure the price will be beyond any any reasonable price. So I will look for a substitution. A short check whether the system works is, I think I connected the scope to pin 6. With the input of the comparator, I have no comparator, and this comes from the emitter of this transistor, from the driver transistor, and we can see that's the result. We have 2 volt per division. Take off the light. And when I move up the trace with the position, then this signal follows. This is the input of the comparator, and when I'm on the top line, I have a voltage of approximately 2.3 volt. And when I go negative, the signal drops. And the other input from the other transistor, from the other driver transistor, from this one, behaves exactly 180 degree different, and this goes to this comparator. So when the signal is negative, this will be positive. I will check it also. Now I'm connected to the other input of the comparator, and when this trace goes negative, this voltage goes positive. So this connection is the discriminator for the negative overscan. When this is over a certain threshold, this gives alarm for the lower diode. And the other one we have seen is the threshold for the overscan in positive direction. So this works, and now I need a replacement for the TL820. That's not so easy, but I have an idea in mind. I had no chance to get this IC TL820 CN on the market. Even a data sheet is not available for free, of course. Maybe there are some dealers who are selling it, but I don't want to pay any cent for it. This schematic is reconstructed, redesigned from the schematic. So we see here two comparators. Each comparator has its separate power supply, plus 12 volt and minus 6, plus 12, minus 6. Two inputs, one output. Here an additional ground connection, which is not needed. I think it's for static purposes also. And this pin is left open. What to do? I didn't find any pin compatible substitution which is available on the market, which can be bought today. I found a double comparator, but it is not a 14 pin, it's only an 8 pin version. It is the LM339B. 393B, sorry, LM393B, which has two comparators in it and which has a common power supply for both comparators. I think there's not a problem here. VCC, and the ground will be used as the minus 6 volt and VCC will be the plus 12 volt. It can be used up to 30 volt as I see for power supply voltage, so it's not a problem. But again, the pin layout is not identical. This is a little bit a problem. So I made a construction, first some theory and then a practical adapter for it. This is the first drawing. This is this 8-pole LM393B. One out, the out of the first comparator is here. That's identical with this. And one in negative and one in positive, which is here and here, are these two pins. So we need an additional wiring. Same for the second comparator. The output is pin 8, that's 2 out. And the 2 ins are here and here. This is a ground connection which will go to minus 6, and this is a positive voltage. Where is it? Here is a plus 12 volt. I could also use this one here, but I've seen there are many wires across the body, so I swapped the orientation. I flipped it around by 180 degrees and I use this version. Imagine this LM393 flipped by 180 degrees. So we have the index for the first one here. We need here a long one, but then we have here only short wires with the output. And the plus 12 volt now is connected directly, which is this long wire is the short wire. So it's a little bit better. That is what I will realize now. I will use this inverse version, to realize it. This is a mechanical solution. I use an experimental perforated board with a 14 pin with 2 7-pin rows. The IC is glued on it with some acrylic glue. And when I flip it around, you can see it from the side. This is a socket, only an IC socket I use to fix it. So the pin rows are exactly centered and vertical as they should be and straight. That is the front vision. The only thing which is important to have sufficient distance between the cut pins and the pins of the IC, that there is no connection, so I shouldn't touch. And now I can wire it. I use some green enameled wire. It is used for cores, ferrite cores and so on. This can be soldered. It's the best solution, and I do it step by step according to the schedule. And some songs of Mango Cherry in the background. Very relaxing. The job is done, soldering is done. You see the green wires, a little bit difficult, but my camera doesn't. Oh, okay, that's still okay. I see. Doesn't have a macro objective, but you see it, and the schematic is shown here. Now it's time to bring it into the scope. The IC, homemade IC, is in place. You see, it's a little bit tricky. This frame here prevents an easy mounting, but it can be done with some patience and some force. And now let's check it. The scope is switched on. Channel 1 is operating, centered line, no overscan. When I go up to the upper limit, the LED is lit, nothing. Lower limit, same happens. When we go to the dual, alternate is okay. It works also with channel 2. When we have this one and we have this one, then we have both. That's what it should be. And now we'll insert a signal, sine wave, and see whether we have the same reaction. We have an input signal 1 megahertz. The scan LEDs are a little bit too sensitive. It's coming too early. The level has to be readjusted. There are trim pots, 2 trim pots. I will readjust it, but in general it works. Overscan with maximum. Nothing. Okay. This is a little bit too sensitive, but in general it works now. It's a good result. Now we can continue. Another topic is solved. The component tester was a little bit too narrow. I found here is a pot to set it. This pot is not documented. It is this pot here. I have an older version of the of this unit. Here it is noted on the rear side. We can't see it, but I have seen it. HM605, and there is a pot. The manual I have is the HM605-1, a newer version. That this pot does not exist. Okay, we have the pot. We can adjust it. Now we have a broad picture, and the vertical height is also now acceptable. That's a reasonable picture. I will check it later with some components, capacitors, diodes, just to prove the function, but I'm sure now that's also okay, and we don't have a problem here. A short test or demonstration of the component tester. The CT is switched on. When I make a simple short circuit in the input, we will have a vertical line. That means only current, no voltage. This is voltage and no current. When you take a resistor, it has 1 kilo ohm. Looks like this, as we can expect. Here I have a diode. The cathode of the diode is connected to Zener diode, sorry, not a diode, Zener diode, 5.1 volt. The cathode is connected to ground, and we see here the typical characteristic. Oops. This is the diode, and here we have the Zener diode in this direction with negative voltage. By the way, this is approximately 12 volt RMS, 15 volt peak or so. And the last object, easiest way, is a capacitor. Capacitor makes a circle. We are operating with 50 Hertz, so I have a rather big capacitor, 6.8 microfarad. When I connect it between ground, we see a circle. Should be a circle, is not a circle. And why is it not a circle? Well, the problem is that the line voltage coming in from the wall outlet is not a sine wave. There are many harmonics on it, especially in an urban environment, so the voltage has a lot of harmonics, and these are disturbing the circle. Theoretically it should be a circle, but it isn't. Okay, that's a component tester. It works. I checked other parameters, sensitivity with the calibrator, it's okay. Time base is okay. I will do only one check at the end of the project. The square wave response of the amplifier. I will align these trimmers here and here to improve the response at 60 megahertz, because when I was searching for the reason of the oscillation, I also tweaked a little bit with the trimmers to see whether it's a question of a bad compensation, but it wasn't a compensation problem. We know it was another problem, so I have to readjust it for this purpose. I will take a signal generator, square wave generator, with a very, very low rise time in the range of I think 1 or 2 nanoseconds. This scope has theoretically 6 nanoseconds or 5 nanoseconds. It has 60 megahertz. This is approximately 5 nanoseconds rise time. So the generator should be much better than these 5 nanoseconds, and 2 nanoseconds are okay. After some short tests, I decided to remove the front panel completely. I have to need access to this input unit, channel 1 unit. The switch was faulty. I could clean it now, but I still have problems. Channel 2 seems to work properly. There are contact problems inside, and I will show you. We have an input signal with a period time. We have a 50 nanoseconds per division. 50, 100, 250 nanoseconds. That's 40 megahertz square wave. I have a square wave generator with a rise time in the range of 1 or 2 nanoseconds. So it's not a problem, but what we see here is a rather bad square wave response. And you see when I touch these knobs here, now it's pictures jumping in the amplitude. This should be better. The true amplitude, this is times 5 when I go back, but you see this is not okay, very touchy. Also other attenuators settings. I show you how it should be on channel 2. Channel 2 is much better. When I move it to the channel 2, that's channel 2. Much better rise time. That's the true response of the signal. I measured approximately 5 nanosecond rise time. That's okay for a 60 megahertz scope. But on channel 1 we have big problems. I assume it's a switch. It's a switch for the pot times 5. I have no access to it. I need to take out this unit. Channel 1, this unit is fixed here with this big nut. This is only a short screw or something to fix it, but this whole unit seems to be fixed only here with this nut. The rest is flexible. Of course this wire has to be unplugged, and this lever here for the switch has to be removed, but that's easy, not a problem. So I will try it. First I will unplug it and remove the lever. The nut on the front is removed. Unit is now nearly free. Unplug this flat wire, flat cable. Then there is only necessary to unsolder the input, which comes from the BNC connector. This has to be unsoldered. this pin, and then it should be possible to flip it out. Now it can be taken out. Hope so. Or not? Yes. Haha. That's it. Rather simple. Now I have access to the whole unit and can clean the switch. It is only soldered here, secured with some solder points, but that's not critical. When I understand it correct, I think it's sufficient to unsolder this solder point here and this, and then it should be possible. Here are only bended flaps to slide out this shield, this case in this direction. There is nothing which holds it back. Okay, I will unsolder here and here. I had to unsolder these 4 connections here, here and here and here with some solder braid. It's the easiest way, and then it can be flipped out this way. Now we have access to the whole unit. The range switch attenuator, and here we have the pot for the variable gain, and this is the switch for the vertical magnifier times 5, as I know, and this switch seems to make the trouble here, the contact. So I have to clean it. A little bit difficult to get access. There are some slots, as I see on the rear side where the axis is, maybe also here inside. I will look, but I'm quite sure that I can clean it. I sprayed some fader loop into the pot and fader cleaner, another loop cleaner, and also the switcher, but I measured it. It was obviously not a problem. The switches, maybe the attenuator switches, I sprayed them also a little bit with contact cleaner. But I found another topic which could have been the problem. This contact here was a little bit bended out, and when there is the shield, maybe there was a contact between this pin here and the shield. There's an input. This could also have caused the bad high frequency response when there's a short of this capacitors to ground. Maybe that this was the reason, don't know. Well, I will try it out a little bit and then reinstall it. Now the input is okay with no problems. I can switch between ground, AC coupling, DC coupling. We have a very good stable picture. When I touch the attenuator, it's okay. Shift is also good. Now we can check the rise time. This is times 10. And position. Let's switch on the grid illumination. I will use this one and this one. It's difficult to see, I think, on the camera. I will switch it off, it's easier for me. We have here the 10% and 90%. It's approximately 4 nanoseconds, assuming that the time base is now okay. In factor times 10 with 5 nanoseconds per division. I'm not sure whether this oscilloscope is good for such a fast speed. I will check it when I reassemble it, but in general it's okay now. And when I compare to the second input, trigger, go to here, same picture, times 10. I also can say it is 4 nanoseconds or so. It should be 5 nanoseconds or less for a 60 megahertz scope. The formula is 0.3 or 300 divided by megahertz is a rise time in nanoseconds. 300 divided by 60 is 5 nanoseconds. We can also use 1.3, then that is gigahertz. Okay, I think now the job is done. In this relation I will reassemble everything, clean it a little bit, and then do some final tests and optimize the rise time, or minimize it, the rise time, to have best frequency response. The response of a square wave signal is optimized. We have here 5 nanoseconds per division. I checked it with a signal generator. It's roughly precise, not very precise. It's a little bit more because the 10 times magnifier in the x-axis is at the high speed not so good. The linearity is not perfect. We can see it when I shift this picture to the left side. It gets a little bit broader, you see. Then you have here 6 or 7 nanoseconds from 10%. Sorry, from the dots. It's 8. When I go with it to the right side, it's also a little bit broader, as I see. So the center is rather precise. It's not so important. I can say we have 5 nanoseconds rise time. That equals 60 megahertz. Well, the job is done. The scope is ready. I will bring it back into the case. I checked the accuracy of the time base. It's okay as far as I see with a simple test with a signal generator. Also the vertical axis, the calibrator is good. So we can finalize now this project. But before we come to our final comments and resume, I wanted to show you the delay option, what it is, how it works. It's a very simple option to delay the time base. It only has one time base, but when we go to the mode normal, then we have operation as we know it. When we go to search, then I have, for example, 1 millisecond, then I can go to any point of the curve. For example, when I want to see, when I'm interested in this part, makes no sense. We have a continuous wave, but okay, assuming we are interested in this part, I'm on search, and then I can go to delay and then increase the resolution, more intensity. So we have it magnified, and and you see with a 10 gear pot, I can slide over the display, but it is a fixed delay time. It cannot be triggered or so, and when I touch it, it jumps. It is a very sensitive solution. Now we have 20 microseconds per division, and the frequency is 1 kilohertz. When I go back a little bit, this pot also needs some cleaning, but I have no access to the pot. It's a 10 gear pot. It is sealed, and it's a rather cheap one, not one of the high quality pots. It's okay, it's a standard of those days. In my eye, this option makes no sense. Let's go back. Well, that's it. And now to the final comment. I'm sure you are curious what happened with the scope. First, to the problems we have found. We had a faulty time-based switch. The contacts on the switch were bended. You have seen the contacts on the top side of the 4 layers of the switch. They were all bended, touching each other. Seems like someone has touched it during repairing it or so, and didn't realize that he's touching and bending contacts. Ugly. Second problem was the oscillation in the vertical amplifier, in the wire output. We had a long wire, which is not good for a 60 megahertz final amplifier. This always or sometimes can cause oscillations. We have inductivity, we have some capacity, we have an amplification, broadband amplification. There's always a frequency which is good for oscillations. Third problem, the X deflection plates were swapped. don't know why the trace went from right to left and not from left to right as it should. And the fourth problem was the IC for the overscan. There was a totally wrong integrated circuit in it with totally wrong number of pins. We replaced it by another type, which made some work, but it works now. Of course, I asked the owner, hey, what happened? Did you do this? No, I didn't do it. Did you buy it? I got it used, he said. Ah, used. Did it work when you got it? Yes, it worked. But you understand the problems which we have in the scope didn't fall down from heaven. They are all man-made, not caused by age or so. Who swapped the IC in the overscan unit? No, I didn't swap any ICs. Did you add the wire to the amplifier, to the vertical amplifier? No, I didn't add it. I really don't understand this. I have an opinion, but I don't tell it. You can imagine what I think. I'm not a fool. I can add 1 + 1 is 2. But the talk to the owner brought no additional knowledge, no revelation or so. Well, I leave it as it is. I give it back to the owner. And I hope he will never touch it. I say to him, use it, but please do not open it. And when you have a problem, ask me before you open it. Before you do any modifications, ask what you are doing. Not do it. That's it. I think this was one of my craziest projects I ever had. Stay healthy, stay tuned. See you on this channel.